So in this section, we're going to understand the core unit of information that exists inside a computer. You can think of a core unit like you do a Lego brick, where, for example, starting from that single type of Lego brick, using your imagination, you can pretty much combine it in different ways to build anything else you really want. So in the same way, in the context of computers, if we have a core unit of information, we too can combine that in many ways to make up all the other information that's stored and processed in a real-world computer. So any software program, tool, or application that you will build is actually composed of this unit of information. And lastly, when you're trying to decide whether something is programmable or a device is programmable, the first thing you make sure is that it's able to perform certain capabilities related to this unit of information. So if we opened up a running computer, what would you expect to see? Would you see miniature versions of the images and text coming from the computer screen? Or smaller versions of the sounds that emit from its speakers? Definitely not, right? What you'd see, in fact, is actually just a multitude of chips, metal objects, and a bunch of wires all over the place. And even if the computer was running, you wouldn't see these wires change in any physically meaningful way. It would in fact be a very boring thing to see. However, inside these wires lies only one thing that really exists in a computer. And it is the only thing that makes a computer useful, and there are a huge number of these kinds of things. And this thing is called a bit. But what is a bit? Well, why don't we take a look at the following statements here. When you flip a coin, it's going to land either on heads or on tails. When you get back an exam, your grade is either a passing one or a failing one. The light in your room could be either on or off. So what's the commonality between all these things? Well, the common thing between them is that there are places or things that can be in either one of two possible states. And that is the definition of a bit, a place or thing that can be in one of two possible states. You can think of it like some kind of physical object that has a size and a defined location in space that you can see or find or point to. And it has some quality about itself that at any given time can be in only one of two possible states, but not both and not neither. And in addition, it can also be made to change back and forth between these two states. So as you can see, a bit actually obtained its meaning from outside the world of computers. It doesn't necessarily have to involve computers at all. However, the computer industry has been using the term bit for so long that it's now pretty much standard that when we talk about bits, we're talking about them in the computer context. So in a computer, well, a bit only differs from what I talked about before in as much as what the thing is and what those two possible states are. In a computer context, the thing is a specific wire that we've designated or that we've identified. And its two possible states are simple. Either it has electricity flowing through it, or it doesn't have any electricity flowing through it. And as you can probably tell from this, a wire can either be one of those things, but not both or neither, right? I mean, a wire can't have both electricity flowing through it and no electricity flowing through it. It doesn't really make any sense. So a bit in computer context refers to wires that are carrying electricity or not, simply put. So to help us understand the bit a little bit better, we're going to draw a simple circuit diagram to get the point across. So we're going to start with our battery here that we're going to put in the bottom of the circuit. We also have a switch that's open that we're going to want to use. Oops. I want to save that image for later. Then we also have a light bulb that we want to be able to use too. So I'm going to go ahead and put a light bulb up there. And now I'm just going to draw the wires to connect that circuit. So you got the wire coming out of the positive end of the battery going into the switch, and the wire coming out of the switch and going into that light bulb, and the wire coming out of that light bulb and back into the battery. So here we have the most basic circuit that you can probably think of. You've definitely seen this type of circuit if you've been in any introductory physics course or electricity course. But basically what we have is our battery that's providing us the electricity. We also have the switch here that controls the flow of electricity for a specific wire. And then we have a light bulb here that will be indicating to us whether electricity is flowing through the circuit or not. So in this example, I want you to take a second and think about this question. Where is the bit in this circuit? If I were to ask you to circle the bit, what would you circle in this case? Well, actually here, the bit is the entire circuit, basically, excluding the light from the light bulb and excluding the battery. And that's because, well, neither the battery nor the light from the light bulb have any electricity running through. Remember what we said before about what the bit is. The bit is just a place or an object or a thing that either is in one of two states, having electricity running through it or no electricity running through it. So the only part of the circuit that can really have electricity running through it or not is the entirety of the wire that I've circled here, as well as the switch that is basically a wire that you've cut or you've connected back together. All right, so this is called the bit in our case here. So we can see here, right, when the switch is initially open, electricity cannot flow through and the light bulb is off. So this means that this bit is off too. And if we want, we can even say its binary state is when it's 0. Now let's say I actually close the switch and enable electricity to flow through now in the entire circuit. Well, then the light bulb would now be turning on because there's electricity flowing through. And now we can say that this bit, still being just the wire that's carrying the electricity throughout the circuit, is on. And so we give it a state of 1. So two key things here to note. Firstly, we can see how in this case the bit is either on or is either off, but never both, because electricity can either be only flowing through the circuit or not flowing through it. And we were able to change between on and off back and forth thanks to the switch. So in this circuit, it was the switch, in fact, that was the toggle, or the location where we would control the state of that bit. The other thing I want to point out is a light bulb. Now think about it. What role is this light bulb playing in our circuit below? Well, what the light bulb is really doing is providing an indication to us or to an observer of the state of the bit. Where an outside observer, seeing the light bulb turning on, would be able to go and say that the bit is on. But the light bulb, however, is not what makes the bit a bit. It was only an indication of its state. Right? I mean, if we took out the light bulb and rebuilt our circuit without it, so just go ahead and fix that. But we would still be able to toggle that bit on or off using the switch. The only difference now being that the observer no longer has any way of knowing whether or not electricity is flowing through that wire. I mean, really, they'd still be able to tell by looking at the switch, but for the purposes of this example, we're assuming that they can't. And so all of that being said, as long as electricity can be said to be flowing through this wire or not, then it is this wire that we call the bit. So there's a couple final notes on how my diagram that I drew differs from real bits in a computer. The first difference is that obviously computers don't have tiny mechanical switches that toggle electricity on and off in our example. It'll become obvious to you why we don't use mechanical switches, but I'm just going to say that it's basically a question of speed. It's a question of speed because compared to what we can use, mechanical switches are actually very, very slow. Especially when you compare it to, say, the speed of electricity, which flows at about half the speed of light. And that is so fast when you compare it to the maximum speed maybe you'd be able to turn a mechanical switch on and off. So in computers, actually, we design bits as part of intelligently created electrical circuits so that we can turn bits on and off with other wires that carry electricity, or with other bits. What this means is that changing a computer bit state from on to off can happen much more quickly than anything that has to be moved physically. And I'm talking billions of orders of magnitude faster. And so to be able to actually get these circuits to do what we want them to do, we use this other component called logic gates, which help move electricity in the right places at the right time, depending on certain conditions. We'll get glimpses and mentions of logic gates throughout this course, but we really don't need to go into much detail to be able to understand what we need to become proper programmers. Because the key of this section was to understand that a computer's core unit of information was the bit. Also, that a bit is just a designated wire somewhere in your computer that either has electricity flowing through it or not. We can definitely get a sense now that to solve the information problem, we're going to be using bits. And I hope you're excited because we're soon going to see how these bits and wires are really arranged in a computer in order to solve the information problem. Let's move on to codes now. So what can we actually do with a bit? So far we know that a bit is only really a place that has electricity running through it or not. I mean, if you think about it, this in and of itself is completely useless to me. Completely useless information that is not meaningful at all. It is only meaningful unless we decide to make this bit represent something else. So for example, if we say that a bit that we want to look at is actually just the wire that supplies power to a store's open sign, we give meaning to the state of this bit. Meaning in the sense that if the bit is off, there's no electricity running through that wire. So the sign has no electricity flowing through it, so the sign is off. And we all know that if we see a store with the open sign that's off, it means the store is closed for business and the door's probably locked, so nobody is going to bother trying to go inside. However, when the bit is on, the electricity is flowing through the sign, and the lights in the open sign are shining bright. And what this means to an outside observer is that the store is open for business. People can go inside the store and purchase items that they want from it. So in this example, if you take the bit being the wire supplying the power to that open sign, we as a society have given meaning to the state of that bit, in that when it's on, the store is open, and that when the bit is off, the store is closed. This example is the act of using a code. Simply put, a code is just a way to tell you what something else means. Basically, making a code for a bit means someone making a list of the two possible states that bit could be in, and associate each specific state to a particular meaning that it represents. So if we take a look at the table here on the right, we're looking at basically a code for that bit that is attached to that open sign. We have the state of the bit, it being on or off. We have a representation of that bit, or a way to know the state of that bit. In our case, we know the bit is on if the open lights are on, and we know that the bit is off if the open sign is off. And finally, we attach a meaning to this state, or to the representation that we observe. In our case, the store is open for business when the sign's on, and the store is closed when the sign's off. You know, you can definitely say that this is just a social norm, and I know that, when the open sign is on, then I can go in the store. But when it really comes down to it, we all follow a code in the society we live in today. But the fact that we live by codes every day is something that I think we do indeed take for granted. So anyways, the code here was something that was written down somewhere as a rule of what a specific bit state means. It's something that has been explicitly thought of, defined, and then shared with the rest of the population to follow as a social norm. But remember, right, the code is not the bit. The bit is that wire or that place, and it's either carrying electricity on or off. The code really refers to how this bit is represented in the outside world and what each representation of the state means and how you should act accordingly. So there's some other examples as well of codes that we use to give meaning to bits. For example, your computer monitor. Your computer monitor basically takes in a set of bits that it reads from somewhere. We'll understand this later, don't worry. But based on what it reads on the bits, based on the on-off pattern of these bits, basically, it displays a set of menus, pointers, images, icons, your mouse accordingly. Another good example of how we use codes to give meaning to bits is actually in programming languages. In a programming language, you as the user write stuff on the computer using the keyboard and write off text, syntax, symbols, and things that you can understand. Then a code is actually applied to the program that you've written to convert the text, symbols, and syntax that you understand into a series of bytes that the computer understands, into a series of ones and zeros. This is often why we call writing software coding, or where the word coding comes from, as we're actually applying a code that many people have agreed upon to represent and work with units of information that live in the computer. So hopefully now we understand that the bit in and of itself contains no meaning, as there's only space in it for whether electricity is running or not. The meaning of the bit is always assigned by the thing that uses the bit, the thing that's external to the bit, that works with the bit that it needs. This means, right, that the same bit being on could mean something in one context and something else in another. So for example, going back to our store's open sign, if instead this bit was attached to a closed sign and provided power to a closed sign, then we'd have the inverse going on, where the bit being on would mean that the closed sign is on, and people outside would see that the store is closed, so they would not go in. And then if the bit was off, the closed sign would be off, and then people would be able to see that they can go in. Although this isn't intuitive and isn't really what happens in real life, I think you get the point.